in. It's pretty straightforward. We'll talk about materials, some areas of the solver, something I'm calling Smart Solver, which is more about improving the solver at the core and functionality that goes across a large number of different workflows. Then, of course, we're always working on contacts. If you're familiar with some of the stuff we've done with Nastran, we are working a lot on solution openness in terms of output with HDF5. We have some pre and post improvements that we've done, and then some things that are generally more specific to some manufacturing workflows, but it doesn't surprise us when our customers find applications of these in other workflows as well. So I'll go ahead and start with materials. Sorry if I rushed it a little bit. I just want to make sure we don't run out of time. We've been working on experimental data fit in multiple releases. I think this is a trend you'll see more and more, is to make sure that as we embark on a functionality, that if we aren't able to get it all in one release, we continue to release as time goes on. If you're not familiar with experimental data fit, please, if you're using our more complicated models, it's definitely worth your time to take a look at it in Mentat. So right now what we've done is we've included cycloplasticity models now in the experimental data fit. The idea is that that will make it easier to use and reduce any potential for user error on the input side. Cycloplasticity, I probably don't need to explain to most people why it's important, but we do see it a fair amount. The implementation is very straightforward. You just select the plasticity in the experimental data fit window, and now you'll have an option for cyclic plasticity. And now we support both the Chbosky and the Hasuguchi model. Here's our comparison that we did, one of our comparisons that showed the experimental fit with the actual experimental data, with the blue being the experimental data and the red being the fit that we made to that. So we had pretty good agreement through multiple cycles. The other thing we did related to materials actually bleeds a little bit into elements was really our support for additive plasticity in the Ehrman elements. You know, if you're not familiar with them, generally for incompressible materials, they really deal with some of the shortcomings of other elements. And now we've added this additive plasticity formulation that we believe it will improve the accuracy and or runtime as well and over the elements you've had used today. You know, so if you're doing manufacturing processes such as forging, offsetting, extension, deep drawing, anything basically where you have a large amount of plasticity, especially when it's constrained for that incompressible aspect. So the implementation, we assign an Ehrman element, and now with that, the large strain preference in the element option, if you go to that, you'll see that it is turned on by default. So you can turn it off, but it's now on by default. So this additive decomposition is really our way forward when we're talking about this type of application. The use case we have is really this forming of a metal block. That's the one we're showing you here with a model with the rigid tooling on the left and the results on the right. But probably the most interesting part of it is on the bottom with the table, where you can see the element types that we ran with the formulations. And if we go over to the right, we can see the effect on the wall time and CPU time. You see that with linear tests, we couldn't even finish the solution. But with element 157, the multiplicative, we could. And then when we switched to the additive formulation, which is again now the default, we had a significant time improvement. So we're very excited to see this, and we're very excited also to hear feedback from our customers on how this functionality is working. Then the Smart Solver. So one example that we have in this release is this localized global remeshing capability. So right now, when you use the global remeshing in previous releases, you had to remesh the entire contact body. What we've now extended as global remeshing is now, even though it makes it seem a little funny because it's actually not necessarily global remeshing in the word of global, is that we now can run that remeshing just locally. One area that that is obvious advantageous is around crack propagation, when you really only need to remesh the area around the crack tip, but the rest of the body is not being subjected to anything significant. So the implementation in the global remeshing property menu for the remesh region, you now have this option where you can specify this region. It can be a set of elements. As I mentioned previously, it can be about a distance around a crack tip, and then it can be a prescribed geometric shape, a box, a sphere, et cetera. And it's compatible with all the existing advanced density controls. So if we look at it in action, you can see here we have 2 cracks, and you can see that we have a region around it of which we adjust the mesh, and a large region which we don't. Likewise, here you can see this is one view and another view of a cut of this double lug with cracks, and you can see that we're only remeshing around the crack tip. The advantageous of this is really depending on the size of your region, the size of your overall contact body compared to what you run before, is we do think you can get some significant runtime advantage. You can see that in the reduction in the memory and the total time it took to run this model. But it's going to vary by problem. So again, we'd love to hear your feedback on exactly what you're seeing in your improvement using this global remeshing, localized global remeshing. The other thing that I will mention as well, the other advantage of this capability is that if you want to track points away from your region of interest, because it's not being remeshed, you have consistency from increment to increment on the results location and where you're pulling data from. The other enhancement that we're calling SMART is the simplifying data transfer for analysis chaining. Really what this is about model section. Not everyone knew about model section before. If you're not familiar with it, again, I encourage you to take a look at it. We've expanded it for chaining analyses so that it's easier to do that. And really, we think this is the preferred option over pre-state now. So if you are using pre-state, we encourage you to take a look at model section. And if you see any issues, of course, always report them to us because this model section is definitely our path forward. So example application might maybe have residual stress and distortion of a part from manufacturing, and then you want to place it into a larger assembly, or you're actually sending it to someone else to do some other analyses on it, and you want that state that happened before. Instead of them rerunning it, they can use the model section to pull the actual state over into the new analyses. So the model section defined as before, and you can do multiples. We've added the option for the frequency of writing to include the end of the low case. It's also a possibility to take a lower order, a 2D or axisymmetric model, and expand it into a 3D. That's already been there. What we do now is we support a bias mesh when you do that expansion. And then we support also additional methods to connect the model section into the larger assembly. So now you can connect the RB2, RB3, and rigid rods in addition to contact, which we've had. So you can see here's an example. So obviously chaining analysis is very important, something we think there's value in. I think I'll challenge us even further to start thinking about this as if this is really a way of modularizing the analysis, because if you look here, each of these are a different model section. They could have been subjected to a different analysis. They could not have been prior to this, so maybe some kind of assembly, manufacturing, state, whatever it may be. And then you can take this and then you can connect it together and build using RB2s, RB3s, rods, contacts, et cetera, and you can build an overall model. So obviously analysis chaining was our initial drive to do this, of moving one part through multiple steps in different analyses. But we should also keep our eye open and looking at this way of actually combining different models into a larger assembly and being able to run that larger assembly with loads as well. I think I'm going to switch now to Bhumi, and she's going to talk a little bit about contacts.
Okay, thank you, Matt. So in contact analysis, we did the enhancements to improve the contact fidelity between rigid surface and deformable body. So let's go through it. So if you recall, in version 2018, we did a lot of enhancements on contact surfaces. So now with version 2019, we have done some significant enhancements in segment-to-segment contact, including rigid STL surfaces and deformable bodies. With this enhancement, our main goal is to limit the penetration to improve fidelity of the contact, which would result into improved accuracy of the contact. So an engineering example of this would be a die forming simulation. So when implemented with this scenario, the STL surface can be used as is, or you can use the faceted surface option. If you still choose to use that one. And then additional contact points are defined by the solver on the rigid body to limit penetration. This means that there is no user input required in this case. It does it automatically free. And then the other area where this is useful is augmentation and associated parameters, previously limited to was limited to deformable contact, and now these are supported in geometric to deformable contact. So, and lastly, this new functionality support delayed slide off between deformable and faceted surfaces. So in cases where you have small gap in your contact surface and you don't want your contact surface to fall into that gap, which would then cause the numerical difficulties and not being able to resolve itself, we now have delayed slide off option to make it easier to go across the small gap. So let's go through an example of this. So here is a simple case example where we have the hydroforming. So you can see here the red surface is the rigid body and the tube is the deformable body. And if you see the results, and if I expand them more into close-up results, you can see that we really did get a lot of fidelity there in that contact, and we did not have any penetration here. So this is to show that we are continuously working on contact analysis to fine-tune it and to make it easy to use. Yes.
And I'll also say that in the venue that I talked before about how we continue to work on our enhancements even afterwards, this is a follow-up from the previous release where we did this with rigid to rigid. And so this is just encouragement to the customers out there that if you see that we've done something in enhancements, we are listening in terms of making sure that we complete our enhancements and take them all the way through. So again, if you see anything you want to see more of, please let us know.
Yeah, sure. Thank you. And then next we will talk about the solver openness. So as code simulation is becoming more important, we realize that it is very important for us to have solver openness. So we're adding some very important enhancements to Mark 2019 release, which is we added HDF5 output. So what is HDF5? HDF5 is basically open source output format, which can be generated as an output result file with Mark. It could be outputted in addition to your T16 file, and the file size is really small, so it wouldn't hurt your file size at the end of the analysis. So HDF5 is basically an alternate open format generated by Mark 2019. It is structured. It is more folder-like thing, folder-like structure, and it has its own schema. So why we did this? We did this in order to improve the integration into downstream engineering processes by accessing output data directly without post-processor. So as you can see over here, it looks just like an Excel sheet, and you can look at your results over there as well, along with your T16 file. A good implementation of this would be if you use our other solver, MSC Nastran, then you can also use the HDF5 file generated from Mark to, they're compatible with each other with MSC Nastran HDF5 and Mark HDF5. So if you have linear analysis with MSc Nastran, and you want to move to MARC, you can do so easily, and it would be the same schema. HDF5 is available to MSc Patran as well, so you can post-process that in MSc Patran. So the outputs supported in this release are the displacements, external forces and reaction forces, and stresses and strain. And the elements supported in this version are the basic TET elements. Yeah. So it's TET elements to the. Sorry, go ahead.
Oh, sorry. The linear and quadratic 2D plane stress, plane strain, axisymmetric, and the linear and quadratic 3D continuum elements are all supported.
Yeah. Okay. So here is a use case that we did where we imported the T16 results into Mentat, and we imported the HDF5 results into Patran. And as you can see, the results match completely. So HDF5 gives you more flexibility for downstream processes, so you can request it in addition to T16 file, as I said. Yeah.
And so maybe if you know from the 2018 presentation, I tend to have some of my favorite enhancements, and this is one of my favorites in the terms of these are the enhancements that can be overlooked sometimes, but are really worth a lot of attention. If you go back to the previous slide, I think the important thing to remember about this output is that it is open. So in the bottom right, that's the HDF view, which is a free available application. And you can actually, as you can see, you can actually look into the results and different aspects of the model that previously would have been very difficult to do, might even have required you opening it up in Mentat or Patran or a third-party post-processor. So really, this is about making sure that you have access to the data you want and you can use that data how you want. What we didn't, we should also note is that there are Python extensions, there are Java extensions, I think there's even C++ or C extensions for HDF5. There's a lot of ways of working with this HDF5 file involving scripting as well. To extract the data you want. So in cases where maybe you already know what the data is you want, you can automate this and it can be extremely fast. And as I said before, you may not even need to open up a post-processor. So it's a very powerful tool. It's a capability, of course, that we can see we're limited in this first release, but like in the other things I've mentioned, we're going to continue to add this release to release, supporting more elements, supporting more outputs. So definitely something to be interested in. And one other note, do not worry about our support for T16. We'll continue to support T16. This is really about an additional format that we think that adds a lot of flexibility and a lot of capability that we couldn't do with T16. Another example of that, of course, being that with HDF5, there's nothing stopping you from writing your own data to that as well. And we're considering that as we're looking forward on where we're going with a lot of things of this openness capability.
We have a webinar on this on our YouTube channel. I will share the link to the webinar as well after this presentation. So next we will talk about the pre and post improvements with Mentat. So first of all, we changed the default multi-level undo to 10, and it can be changed from 1 to 50. Next, if you remember, we do have the color assignment for different contact bodies. So we extended it now to material and geometric properties, so you can define different colors to different material properties or materials. Next is the default maximum and minimum values for contour plot. So as you can see in this image over here, we have the default maximum value and then the node number next to it and minimum value as well, and then the node number next to it or element number. And then here we also have the plot name and those sort of details. And then we also added right mouse button options for show all, hide all, or show only for curved surfaces, elements, model sections, solids, contact bodies, and sets. Last but not least, we added an option to reduce the data points. in option in the table menu. So as you can see over here on the left, on the right, it's actually, you can see that you have 200 data points, and then you can reduce it to 11 data points, and you would not lose any accuracy in this case. So these are all the enhancements with pre-post processing. Next, I will give the control over back to Matt.
Okay, great. We'll talk next about some of the manufacturing workflow improvements we've done. So we've expanded on our trimming options. We've had a trimming option, and we wanted to expand that further to add a little more capability. And this is, again, one of those functionalities where I think that we should, we're definitely being aware of looking for creative ways that people might use this functionality to maybe even go beyond what would just be replicating manufacturing process. So if you'd like to know more, I won't talk about it here, but I'd definitely be interested in ways that we could use this. You can simulate material removal fast and efficiently. Now, with the trimmer, you can option to remove the material inside or outside the trimmer. So this is definitely makes it easier if it's easier to define the surface inside or outside of that you want trimmed. You can retain the trimmed out region as well. Maybe you just want it separated out. We can imprint the mesh of the trimmer onto the trimmed part if we're using a 3D mesh to do the trimming. And now we've extended it to our trimming tool to now have the trimming actually defined as a faceted surface, a contact body, or the 3D mesh in addition to a rigid body. So if we look at these functionalities, you can see this actually adds a lot of flexibility in terms of any situation where you want to break apart a region or a mesh under more specific user control versus having it happen due to some criteria. And these are just some of the simple use cases that we've done. The upper right, you can see maybe the HCM5 webinar come up. So there's a lot of options there, and it's a very flexible tool, and I encourage you to take a look at it. The other enhancement is really on welding simulation, but this actually has applications elsewhere when it comes to inherent strain. We know additive manufacturing also tends to use inherent strain, so this functionality, even though we're presenting it here in the welding context, could apply elsewhere as well. And so we just need to extend those in the inherent strain options. If you're involved with welding, you know about the residual stress and strain associated with that. The key here is that if you have a non-flat surface, it makes this inherent strain application a lot easier. So the implementation we've done really is that the modeling, you can either have it defined directly by the user, or you define the inherent strain boundary conditions, and then you define the inherent strain values for selecting entities. You can use tables for time dependence, or the big improvement related to non-flat surfaces is you can use a local material system. And then you can also have this defined using weld kinematics. If that's how you're defining your welding, you can set up a weld path and the weld filler as you did before. You can define inherent strain boundary conditions, and then, like as you did before, the inherent strain values and the variation using the table data, the weld torch data, and then you have other options on applying that inherent strain definition to substrate elements, and then then the simulation will introduce all of the inherent strain applications. So it's a more automated way of doing it when you just want to know, you know the path, but you don't want to set up all the details. So this is a use case we have, which is the welding of a propeller shaft bearing. I think the important parts to look at is here are all the coordinate systems that if we were setting this up in a global would be a real pain to set up. Now that we can set these coordinate systems in the local material system, now we can have this whole welding operation simulated in a way that is much easier for the user, and it runs faster. We always, of course, can use the traditional thermal structural kind of approach of doing this kind of simulation. Inherent strain is generally just much faster, what it gives up in a little bit of accuracy makes up in terms of speed. Another enhancement we've done is this multiphysics path to model the chemical diffusion. So we're modeling the mass transportation due to a concentration gradient or convection. We use second Fick's law. Some of the applications of this might be carburization or a moisture transfer process. Implementation, as I said before, we use second Fick's laws. We now have the following couple analysis types. We have thermomolecular diffusion, structural molecular diffusion, and a thermal structural molecular diffusion process. The use case here is we're looking at really some carburization taking place. We have temperature profiles as we move from left to right. We submit temperature and then the cool down. So it's at peak temperature at 3,600 seconds, and then cools down completely at 7,200 seconds. And so this is our temperature profile, and we can now see what was our molecular concentration during that. And of course, it doesn't stop at the peak because there's still some diffusion out being taking place at 7,200 seconds. And then if you've been looking closely, we have been doing a lot when it comes to this non-homogeneous current distribution, electromagnetics, a lot of stuff with induction heating. So we've now added the ability to look at circular thick-walled mesh coil definitions because the current becomes non-uniform. So of course, induction heating with thick coils is the primary application for this. We now have a thick-walled coiled mesh option that's added to the existing menu. We use the source current density as a boundary condition, and then what we do is an iterative process where the solver calculates the total current distributed in the coil. It's compared with the requested current, and then it's scaled to really make sure that we are at the distribution that's expected along with the total requested current. So this iterative process is something that we use here, we use elsewhere, we want to continue to use it. I want to say that I'm very interested in what similar things this iterative process can bring to us in terms of the solver, because it's something that maybe we can use elsewhere, leverage elsewhere as we're moving forward. And so here's the use case. We have some cyclic shown with the 3D model and some thick-walled induction heating elements. And we can see the current density that at the end in the thick-walled induction heating element, and then what happened in the actual model as a result of that non-uniform distribution. So in summary, we talked a little bit about some of the material stuff we've done. The Smart Solver, which again is a category that normally we might put these things under different categories, but here I'm trying to bring them together to make sure that we're paying attention to what we're doing across multiple workflows. Contact as well, and we always, again, continue to improve Contact. This solution openness with HDF5, which is, of course, my favorite functionality in terms of not favorite is the only one I pay attention to, but it's the one that I think that you should pay attention to if this is the first time you're seeing it. Pre and post improvements that we're doing with Mentat, and then the manufacturing workflow improvements that we're doing, and we'd be very interested in feedback on any of these. Again, as I said, some of these are either finishing up or in the middle of the process of us getting to the final state of a full function capability, or in some cases, they're at the beginning of them. But they all yield value in their ways, and so I encourage you to take a look at them, and of course, always provide us the feedback, because that's what encourages us to move forward with some of these.